So the next part of the discussion here is photochemical decomposition. Photochemical decomposition. If you go for photochemical decomposition, here catalyst, reactants gets converted to products in the presence of sunlight. The sunlight, mathematically we give it in the form of h mu. H mu is nothing but the frequency of radiation, h is the Planck's constant and mu is the frequency of radiation, and we can just call this as a photochemical reaction. This is photochemical reaction. This is a photochemical reaction. Take some examples of photochemical reaction. One is, the best example is, we can take the decomposition of hydrogen iodide gas in the presence of sunlight, that is h mu. Sunlight acting as a catalyst, it gives H2 gas plus I2 gas. That means 2 moles of hydrogen iodide gas is decomposing to give hydrogen gas plus I2 gas. Sometimes you can also take ammonia gas, 2 moles of ammonia gas in the presence of sunlight, that is H mu, it gives 1 mole of nitrogen gas plus 3 moles of hydrogen gas. All these comes under the photochemical reactions. We call them as photochemical reactions. Photochemical reactions or photochemical decomposition, because here the sunlight is acting as a catalyst. Sunlight is mathematically given by h mu, where h is the Planck's constant and mu is the frequency of. So the next part of the discussion here is displacement reactions. If you go for displacement reactions, if you go for displacement reactions, that is it's like this principle. If you go for principle, more reactive metals displaces less reactive metals from its salt solutions. So for example, if you take the reactivity series, of metals, you find that if you take copper if you take, and zinc if you take, and lead if you take, we can see that copper and lead are more reactive, and zinc and lead are more reactive, and copper is less reactive. So if it is less reactive, then you can take one equation, zinc solid plus copper sulfate aqueous, which is bluish color solution. It immediately, here zinc oxidation number is 0, in copper sulfate copper oxidation number is +2. So this copper is getting reduced. Zinc is acting as a reducing agent. If it is acting as a reducing agent, then copper sulfate, it gets converted to copper solid plus zinc sulfate aqueous. This is, you can say that blue color fades. In the case of copper solid, blue color fades, and the zinc sulfate is going to become white precipitate. So here this is one type of reaction where that means zinc is reducing the copper sulfate to copper and by itself it is getting oxidized. Zinc, in zinc sulfate, zinc is +2 and copper is 0. This is one type of reaction. Then you can go for one more reaction if you want. That is likewise, if you take iron, if you take iron solid and if you treat it with copper sulfate, here iron solid, when it reacts with copper sulfate aqueous solution, this iron gets converted to ferrous sulfate and copper is getting reduced to copper solid, and here you find that iron is going to become brownish colored. It appears a brownish color solution. This is bluish color, and this color fades here. Color fades. Less bluish color is obtained because it's a solid. From this equation, it's very clear that between iron and copper, you can see that iron is more reactive. Similarly, between zinc and copper, that is, zinc is more reactive. So the next part of the discussion is double displacement reactions. Double displacement reactions. If you take here, when two or more atoms or groups of a compound react, exchange of radicals means cations or anions. Cations or anions occur, resulting in formation of a new salt and a precipitate. PPT stands for a new salt, PPT stands for a precipitate, PPT stands for precipitate, and a new salt is formed. Suppose, for example, we take sodium sulfate aqueous plus barium chloride aqueous, it gives barium sulfate in the downward arrow plus sodium chloride aqueous. So what you are noticing here is this is a precipitate. It's a white precipitate. So for example, what are the ions involved here? For example, sodium sulfate contains Na plus and SO4 2 minus, and barium chloride contains one barium ion and one chloride ion. So there is an exchange of radical is taking place. The sulfate ion, which is anion, is going towards barium, and the chloride ion, which is anion, is coming towards sodium cation. So therefore it is resulting in the formation of, this results in the formation of, one is sodium chloride comma barium sulfate. This is called double displacement reaction with exchange reaction. This is example 1. Now example 2, suppose, for example, example 2, if you take, that is, silver nitrate reacts with the barium chloride aqueous. Again aqueous, you get here AgCl precipitate, white precipitate plus barium nitrate, aqueous. So what are the ions taking place here? In silver nitrate we have one Ag plus ion and one nitrate ion, and in barium chloride we have one barium ion plus one chloride ion. So exchange of ions are taking place here. So barium is being exchanged towards nitrate, and silver ion is getting exchanged to chloride ion. So this is the kind of exchange taking place, and therefore you find that here we get two compounds. One is silver chloride, and the one is barium nitrate. Silver chloride and barium nitrate, exchange of ions are taking place. So in this way we can study about the displacement reactions, wherein which the exchange of radicals are taking place between the reactant molecules, such that one precipitate and one new salt is formed. So here this is the precipitate and this is a salt, soluble salt. Again this is soluble salt, insoluble precipitate. Wherever we are calling it as precipitate, it is insoluble. Wherever it is soluble, that means that salt is completely soluble in, it is able to dissolve itself in water. So if you go to the same displacement reaction, one more last example let us take. That is, I am taking here, that is the same displacement reaction, example 3 of displacement that is double displacement reaction, that is lead nitrate aqueous plus potassium iodide. Aqueous gives rise to PbI2, precipitate we get, plus PbI2 precipitate we get, and potassium nitrate 2 moles aqueous, which is soluble salt. So it is very clearly understood that, of course you need to balance the equation. It's very clearly understood that the lead iodide is forming a insoluble precipitate. It is going to form insoluble precipitate. So here when you go to the precipitate, it forms a color. It can give the white precipitate, insoluble white precipitate, and here it is very clearly understood that these are some of the most prominent examples of the double displacement reactions. Here also, in the case of lead nitrate also, we can have one plumbous ion, we have one nitrate ion, and here we have one K plus ion, and here we have one iodide ion. So here the iodide is getting exchanged to plumbous ion, and the nitrate is getting exchanged to K plus ion. So this comes for the double displacement reaction. Next, after this we will go for the next topic, that is we can go for that is redox reactions. Redox reactions. In redox reactions, what is the meaning of redox reaction? Red ox. In this only meaning is there. You cut the word into two halves. That is redox reaction, a chemical equation involving both oxidation and reduction. The redox reaction which involves both oxidation as well as reduction is redox reaction. So reduction involves gain of electrons, addition of hydrogen, and sometimes there is a decrease, gain of electrons. It involves gain of electrons, addition of hydrogen. This, therefore the reduction, sometimes it's also called electronation. It's also called electronation. Go for oxidation. Loss of electrons, loss of electrons, addition of oxygen, also called de-electronation. Also called de-electronation. So here if you take, suppose for example, if you are taking reduction and oxidation, a reaction can involve both oxidation as well as reduction. For example, I can take some reactions, for example, okay, so we will study the reactions between reduction and oxidation. So here if you take the equation that is cupric oxide when treated with hydrogen. Cupric oxide is a solid, hydrogen is a gas. When treated with hydrogen gas, it forms Cu solid, copper solid plus H2O liquid. So what you are noticing here this hydrogen, we are trying to add hydrogen. H2 is added. H2 is added and oxygen is removed. H2 is added and oxygen is removed. Because oxygen is removed and H2 is added, when you add H2, when you are adding H2, it means that this is reduction. You can take this as reduction, and here oxygen is being removed. When oxygen is being removed, you find that this is also reduction. That's because removal of oxygen is reduction, addition of hydrogen is also reduction. So therefore, in a nutshell, I can just explain again, once again I can give you the explanation. Cu plus H2 gives rise to Cu solid plus H2O liquid. So here hydrogen is acting as a reducing agent. Copper oxidation state is +2. Hydrogen oxidation state is 0. Again copper oxidation state is 0 and hydrogen oxygen oxidation number is -2. So if you take the hydrogen, if you are taking hydrogen here 0 to, this is from +2 to, you can take it like this. What we can do is, I will show it like this to make you to better understand. Take the oxygen and take copper. So from oxygen, here in cupric oxide, oxygen is -2 oxidation number, and here oxygen is -2, so there is no change in the oxidation number. But if you take hydrogen, if you are taking hydrogen, it is +2. So again, if we take +2, 0 to +2, it is oxidation. 0 to +2 is oxidation. 0 to +2, that is the hydrogen molecule oxidation number is 0. 0 to +2, increase in the oxidation number, so oxidation. In cupric oxide, copper oxidation number is +2, it is getting decreased to 0, so this is reduction. From oxygen to oxygen, no change in oxidation number. No change in oxidation number. No change in oxidation number. So this reaction therefore very clearly explains, that means in the given equation, both reduction as well as oxidation is taking place parallelly. Suppose one more example I would like to give you. This is example 1. Example 2, you take zinc oxide solid plus carbon solid, you get zinc solid plus carbon monoxide gas. So here zinc is +2 and here zinc is 0 oxidation state. So +2 to 0 reduction. carbon is 0 here, here the carbon is +2 oxygen state. So we can take here carbon to carbon 0 to +2, it is oxidation reaction. It is oxidation reaction. So this is a perfect example of the redox reaction taking place simultaneously. The reduction reaction is taking place, simultaneously reduction is taking place, and simultaneously oxidation is taking place. Here zinc in zinc oxide, zinc is getting reduced to zinc, and the carbon is getting converted to carbon monoxide. So both oxidation and reduction, both of them are involved parallelly, therefore we can call it as the redox reaction. So the next part of the discussion, that is corrosion. Corrosion is simply also called corrosion, otherwise it is also called rusting. Rusting is nothing but chemical oxidation of metal surface in the presence of moisture. So in other words, if you take a piece of iron rod, say this is a piece of iron rod which is uniform in its surface, and this is the moisture. This is moisture. Moisture contains O2 plus water. This is piece of iron piece. So during corrosion, what we notice is the metal oxide when it comes in contact with the X number of moles of water liquid plus O2 gas, immediately it forms Fe2O3 dot XH2O. Here this is light brown color. This is going to become reddish brown color. So when you say chemical oxidation, rusting also here means this is chemical oxidation. When you say chemical oxidation, iron solid plus O2 gas gives rise to Fe2O3. So here the iron, when you are passing oxygen, it is getting rusted. So whenever a metal is converted to metal oxide, it gets rusted. So here more oxidizing metals, more reducing metals, they can reduce the less reducing metals in the case of rusting. Here rusting of iron in the presence of moisture, that is O2 plus H2O, we call it as corrosion. Rusting of iron is corrosion. Then conversion of silver, which is grey, to Ag2S, that is black. We call this process as tarnishing. In other words, that is silver, which is a solid, it reacts with sulfur, again it's a solid, it becomes Ag2S, which is black. Once the silver, which is in grey color, converts to black color, it is called tarnishing. Also, more reducing metal more reducing metal oxidizes and reduces metal oxide. Example, zinc plus cupric chloride. Zinc gets corroded. Zinc chloride and copper is prevented from corrosion. This is called sacrificial metal reactivity. Sacrificial metal reactivity, we call it as sacrificial metal reactivity. More reducing metal gets oxidizes and reduces less reducing metal oxide, less reducing metal oxide or metal chloride, because this is a metal chloride. So this is metal chloride. This is a metal chloride. Metal oxide you can take or metal chloride you can take. Metal chloride. So the next part of the discussion is rancidity. If you go for rancidity, that is fats and oils when oxidized they turn rancid. Obnoxious smell or odor. So to prevent this obnoxious, to prevent this rancid nature of fats and oils, what we do is for prevention of rancidity is done by adding antioxidants. Antioxidants to fats and oils. Antioxidants for fats and oils. So if you go for this antioxidants, anything which prevents the decay, that is, you can add vinegar. We can add small amount of vinegar. We can add a small amount of flavoproteins and so on. All this will prevent the rancid nature of the oils and fats. So here let us solve some questions in metals and non-metals. Let us solve some questions. That is exercise in metals and non-metals. Non-metal exercise in, you can take it like this, exercise in chemical equations and calculations. And metals and non-metals. A small questionnaire we are going to do. When magnesium reacts with, first question, magnesium magnesium when reacts with air, the products obtained. The products obtained are. So the reaction is very simple. Magnesium is a solid. It reacts with air because air is a mixture. So air contains both oxygen as well as nitrogen gas. So there is a possibility for it to give both magnesium oxide plus magnesium nitride, Mg3N2. Or the same reaction you can write magnesium solid plus oxygen gas gives rise to magnesium oxide solid. Balance the equation. Take 2 over here, take 2 over here, and magnesium solid plus nitrogen gas gives rise to Mg3N2 solid, magnesium nitride. Balance the equation. Take 3 over here. This is magnesium nitride. And this is magnesium oxide. Magnesium oxide. Again, take magnesium oxide. It's a solid. You dissolve it in water. Liquid. It forms a base. Magnesium hydroxide, aqueous. It's a base. Again, magnesium nitride, if you take solid plus H2O, liquid gives rise to magnesium hydroxide, aqueous plus ammonia vapors. Balance the equation. Take 2 nitrogens here, so assign 2 here, 3 magnesium, so assign 3 here. I think the number of oxygens are 6, so take 6 over here. The reaction is automatically balanced. The reaction is automatically balanced. So the second question is Fe2O3 solid plus aluminium solid gives rise to Al2O3 solid plus iron solid. So in this is the equation which is given to us. First one, balance the equation, mention the type of reaction, mention the type of reaction, and identify species getting oxidized and reduced is the question. So first question again, if you want to answer it, so I repeat here, balance the equation. If you want to balance the equation, here only we can balance it. There are 2 irons and here we have 3 oxygens. We have only 2 aluminiums, 3 oxygens. So I think if I place 2 here, the reaction gets balanced. There are 3 oxygens, here we have 3 oxygens. Okay, fine. There are 2 irons, here there is only 1 iron. So the reaction is already balanced. So that means 1 mole of ferric oxide reacts with 2 moles of aluminium to give 1 mole of aluminium oxide and 2 moles of iron. The reaction is already balanced. Mention the type of chemical reaction. This is nothing but the chemical displacement. Mention the type of chemical equation means chemical reaction means here only we can give the answer. This is chemical displacement. We can say that the reaction is chemical displacement because here the iron in ferric oxide, the iron is getting displaced in the form of iron. The ferric ion is getting displaced in the form of iron from its oxide. This is metal oxide, and this is metal. So metal is being separated from metal oxide, and here aluminum is acting as a reducing agent. Identify the species which is getting oxidized and species which is getting reduced. Identify the species which is getting oxidized and the species which is getting reduced. We can say that here the iron oxide is getting reduced. The iron oxide is getting reduced, and aluminium to aluminium oxide. So here aluminium is getting oxidized. Aluminium is getting oxidized. So therefore it's a sort of redox reaction. Question number 3. Why color change occurs when iron rod dipped in copper sulfate solution? When iron rod is dipped in copper sulfate solution. So therefore what I am doing here is I am just taking a vessel wherein which here this is copper sulfate, and here we are dipping an iron rod. It's a piece of iron rod. This is brown color. Here what is happening is once iron is dipped in copper sulfate, the reaction takes place like this: iron solid plus copper sulfate aqueous. This is dark blue. It becomes ferrous sulfate aqueous plus copper, pale blue, and this is going to become greenish brown. That means here what is happening is the copper is getting reduced. In copper sulfate, copper is getting reduced. And here iron is getting oxidized. The reason because of that, you find that means the iron is trying to reduce the cupric ions in copper sulfate to copper. That is why you find that there is a change in the color. You can see that there is an intense greenish color, and here there is a dip in the copper sulfate solution to pale blue color. The reaction takes place, and after once the reaction is coming, it becomes the intense greenish brown color appears. Intense greenish brown color appears, and this is how we can answer the question. So the next part of the question is, give an example of decomposition reaction involving absorption of electrical energy. So here if you take the answer for this is, if the electrical energy is converted to chemical energy, the process we call it as electrolysis. Example, you can take water, liquid, 2 molecules of water, subject it to electrolysis, electrolysis, it gives 2 moles of H2 gas plus 1 mole of O2 gas. 1 mole of O2 gas. So this is electrical decomposition reaction. Here water is getting decomposed. So the 2 molecules of water or 2 moles of water is getting decomposed to give 2 moles of water is getting decomposed to give 2 moles of hydrogen gas and 1 mole of oxygen gas. Here perfectly it is utilizing the electrical energy. Electrolysis involves utilization of electrical energy. Utilization of electrical energy.
If you like this video, please give a thumbs up. Please subscribe to our channel to get more videos on CBSE syllabus.